Hi everyone, my name is Peter and welcome to my channel, Data Engineering in Practice, where I would like to share some of my data and analytics engineering work with you by presenting projects and different data solutions I've been working on lately. And before we dive into project details, allow me to clarify what this channel is and what it is not. Basically, I made two assumptions about my work here. First, these videos are not some specific framework tutorials. And second, I try to put my data engineering and analytics work into broader business context. Okay, first assumption I mentioned. As I said before, videos I'm going to share with you are not some specific framework or service tutorials. I'm not going to guide you step by step how to use different data tools. There are, as you probably know, plenty of great tutorials, videos, documentations, and other sources online where you can learn how to use tools like Spark, Airflow, MongoDB, Python, SQL, and so on. My videos, on the other hand, are more like project demos. And the second assumption I made, well, each project on this channel represents a separate data architecture designed to solve some, well, hypothetical but still business or organizational problem. I assume that every data product should be created with some kind of clear business objective in mind. And behind every solution, there are always some upstream and downstream stakeholders with their specific needs, expectations, goals that should be carefully considered before we start the most fun part, which is of course technology. Okay, in every project demo, I will try to guide you step by step through the entire data engineering process as I personally understand it. And what are those steps? Well, in every video, it's gonna be, well, similar. I will start by defining business problem along with some stakeholders' needs and pain points. And based on that, I will outline the system's functional and non-functional requirements. Next, first step, I will give you some high-level overview of the system architecture, the tools and technologies I choose, and how I try to integrate them to ensure that system meets stakeholders' requirements and solve some core business problem. After that, we will dive into implementation details, including the code, technical challenges and problems I've been dealing with, and some solutions I choose to address them. Each video will also include some practical walkthrough where I will try to demonstrate how the final data product works in action. Finally, the last step, I will try to summarize the project and highlight the most important, at least from my perspective, lesson learned and some key takeaways that I strongly believe can be applied to some real world data engineering scenarios. So I really hope you will enjoy my videos and I really hope you will find something useful in it. And let's start. Okay, so I called my first project Food Trends Analytics Pipeline. And why Food Trends and why Analytics Pipeline, you ask? Well, food trends, because in this project I process global food production, consumption, trade and pricing data collected from public APIs and external data sets. Two data sources I choose was World Bank, Open Data, and FAO stats, so Food and Agriculture Organization statistics. And basically I selected 5 most frequently consumed agricultural products in the world, which are soybeans, corn, rice, wheat, and potatoes. And why analytics pipeline? Because it is an end-to-end serverless cloud-based solution. Basically, the project combines ETL pipeline, so extract, transform, and load approach, cloud architecture, some data warehousing, some data validation, CI/CD workflow, and as a final data product, well, BI dashboard in Tableau. In my project, I use AWS environment, as you can see, but such projects can be, as easily implemented using services and tools offered by other cloud provider like GCP, Azure, or SAP. Okay, but before we jump deeper into the technical details, let's check for whom and why this system was prepared. So let's check the business problem. Okay, so a scenario is something like that. A global FMCG company specializing in food production, distribution, and commodity trading is, struggling to react quickly to changing market conditions and customer trends. To create an effective business strategy, this company analyzes top global food and agriculture product metrics like production, consumption, trade, and by trade I mean export and import, and of course pricing data to support different decisions related to business areas like sourcing, supply chain management, pricing, inventory planning, and of course market expansion. However, the problem is that data are scattered across multiple sources, multiple CSV files, public data sets, and external APIs, while reporting processes are largely manual and Excel based. And as a result, main problems in this scenario are, well, first of all, market trend analysis takes too long because of different data sources, different data formats and models. Second problem is that analysts spend significant time on manual data preparation. Reporting is inconsistent across different teams. So we have different reports in supply chain team, different in analytics team, and so on. And last but not least, C-level management or decision makers lack some centralized and up-to-date analytical insights. Okay, to address these issues, the company needs some centralized analytical platform, which will be capable of automatically collecting, transforming, and storing and visualizing, of course, global food market data in a scalable and, of course, cost-effective way. Okay, who are main stakeholders in this scenario? Well, The main stakeholders are analysts, business analysts, commodity analysts, BI analysts, for example. Second main group of stakeholders are supply chain teams. They need data for planning and analyzing supply chain. Market intelligence teams, and also commodity traders. So basically people who buy and sell stuff. And of course, C-level management as usual. Okay, and what are the main problems and pain points? First problem is that data are scattered across multiple sources. As I mentioned before, well, data are extracted from different public APIs, different data sets, and they are in different formats, different models. Basically, this process in this hypothetical company is manual. So it's manual CSV processing, and as you probably know, CSV is not the best format for data processing or data analysis. Next problem and pain point, there is lack of centralized reporting. So different teams, different reports, different report formats. There is also no automated data refresh. Right, data are changing all the time, and we need to refresh them. And the company analysts are refreshing them, manually. Next pain point. This solution is has limited scalability. Because of the spreadsheet workflow. Okay, so these were basic problems. Okay, and so far, well, hypothetically speaking, after conducting some consulting work, after conducting some surveys and interviews with defined stakeholders, gathered information showed that this future data solution should meet some functional and non-functional requirements. And let's start with functional requirements. This functional requirements answer the question: what should the system do, right? And what are defined functional requirements? Well, the system should, first of all, automatically collect data from different APIs and external data sources and combine them somehow. Second, this system should store both raw and transform data. Additionally, it should clean and standardize data sets, because as you will see in a moment, these data sets are dirty and have different formats, so they need to be cleaned and standardized. And another functional feature is that data should be loaded analytical data into a warehouse. And the system also should support reporting and dashboards, because that was the main pain point of stakeholders. There is no some integrated tool for reporting and dashboarding. And it should also provide some historical analytics. Okay, next thing we should define are non-functional requirements, and this This element of the system asks the question, how should the system work or behave? Okay, so let's define non-functional requirements. Well, as every system probably, this system should be cost effective and in use for periodic analytical workloads. Why? Because data does not need to be processed in real time in this scenario, and data sources are updated monthly actually for World Bank price data, and for FAO stats data even once 3 months, half a year, or even yearly. So the system should avoid always on infrastructure. So basically a serverless architecture based on, for example, S3 and Lambda functions should reduce operational costs for scheduled and or even driven batch processing. Next non-functional requirement is scalability for growing historical data sets. Why? The platform, because the platform should handle additional data sources or data, different dates, countries, products, or different KPIs, indicators, and it should do that without redesigning the whole pipeline, right? And this scenario, I use S3 as a data lake. And S3 provides scalable storage, while these modular ETL scripts, which I show you in a moment, allow new datasets to be added as separate processing components. Okay, next non-functional requirement, modularity, of course. Why? Because since data sources differ in structure and may change over time, so this ingestion, transformation, validation, and loading processes should be separated into independent models. This makes it easier to debug failures, or they will be failures probably, and update only one part of the pipeline instead whole system. Okay, next, well, data reliability and validation. Okay, because this data will be used in this very important decision making, business users need consistent KPIs for pricing, production, trade, and so on. So the system should validate, transfer data before it is loaded into data warehouse, to reduce the risk of incorrect dashboard results. Okay. Fifth non-functional requirement, traceability and recovery. And this means that raw data should be stored separately from transformed data, so that the pipeline can be rerun, for example, if I don't know, transformation logic changes, or for example, data quality issues are detected. Okay, we almost done, but 3 non-functional requirements to go. Next one is BI performance and structured reporting. So the final data model should support efficient analytical queries and Tableau dashboard, and because of that, some kind of warehouse with, for example, star schema with fact and dimension tables should be created, and it should provide a clean structure for business reporting. Okay. Next one, is security, of course, and configuration management. I suppose every data system should be secure and configured in this area. So basically, the credentials and configuration of the system should not be, hard-coded in the code base. Since I use AWS environment, so AWS environment variables and EIM, AM based access should be used to separate code from secrets and permissions of some kind. Okay, almost done. I think it's the last one. Last non-functional requirement is automation and production readiness. So the pipeline should, reduce manual Excel or some other spreadsheet tool-based reporting by automating ingestion, transformation, loading, testing, validation, through Lambda or GitHub Actions, which I use in this system, and some kind of monitoring tools like AWS monitoring tools. Okay, so these are all basic functional and non-functional requirements of this system. And based on these requirements, I design, as I mentioned before, serverless and AWS-based ETL architecture, combining data lake storage, automated ingestion and transformation pipelines, PostgreSQL data warehouse on AWS RDS, and Tableau dashboard. And now that we have defined business problem and system requirements, let's see now how the system architecture looks like in big picture, and then we jump into technical implementation of this solution. So, architecture overview. Okay. So now I'm going to show you my systems architecture. This is my GitHub account, and this is a project repository. And in this repository, I have this beautiful system architecture diagram. Yeah. Okay, every full data system should consist of several common parts or layers, like data sources, storage, ingestion, transformation, or serving part. And additionally, you have to consider system features or undercurrents like orchestration, security, data ops, data quality, or fault tolerance. Let's start with data sources. As I mentioned before, I have two data sources in the system, World Bank API and Food and Agriculture Organization data sets. So it's here. Then we have a storage layer. I basically implemented an S3 based data lake with separation between row and transform zones, and this storage layer is represented by this green two squares. I have one S3 bucket with two prefixes, so it's one bucket with row zone prefix and transform zone prefix. And first, data are extracted from data sources and stored in row layer. And then, after some transformations and data cleaning, data are stored in transform layer over here. And why this separation? Because this separation improves traceability, debugging, and some possible future extensibility, for example. Okay, then we have ETL processes, so ingestion or extraction, transformation, and load processes. And this ingestion, transformation, and load layers were implemented basically in Python using modular ETL scripts executed in Lambda function. Basically, Lambda is a serverless computing service provided by AWS. Why serverless? Because I selected this approach because, well, the project processes periodical or periodic analytical workloads rather than some continuous streaming data. So it doesn't have to be all on all the time and burn money. Okay, as you can see here, this is a ETL approach. So first data extract from data source, then I conduct some transformations, and after that stage, data are loaded into the final destination, which in this case is data warehouse over here. And why ETL are not ELT or other data solution? Well, first of all, with ETL we have better control over schema consistency, and it is crucial for data warehousing. So loading data into the data warehouse requires clean and transformed data sets with some predefined data model. And each ETL step is executed as a group of independent AWS Lambda functions. Here extraction, here 5 functions for transformation, and 5 different functions, Lambda functions for load data into the data warehouse. Okay, and since this in this scenario I have different data sets and different data sources, each data set is transferred separately over here. And after transformation, each table is loaded separately into the data warehouse, as I said before. I have 1 function for data extraction, 5 Lambda functions for transformation raw data and loading them into the S3 transform zone, and also 5 Lambda function for loading prepared data into the data warehouse. And since AWS Lambda requires not only the code but also deployment packages, every function is deployed as a zip archive, which contains first of all Python source code over here for every Lambda function, and I use, as you can see, different Python libraries for different tasks, including, for example, pandas for data transformation, requests for API calls, Boto3, which is actually a AWS SDK for Python. So interact with AWS services like Lambda, RDS, or S3. I also use PyTest for some code unit test and PsychoPG2 to establish connection to PostgreSQL data warehouse and execute some SQL operations. So every deployment package, Lambda deployment package, contains source code, but also some project dependencies and helper models. I will show you in the next section how this code and how this helper function looks like. Okay, and this approach allowed me to keep the architecture modular and simplify deployment and updates of individual ETL stages. And as you can see down here, the pipeline is schedule or event driven. it's not like full orchestration used in this project. I use Amazon EventBridge for cron scheduling, but also this Lambda functions have event-driven triggers, which I show you later also. What else? I also use AWS budgets, for cost management, and AWS CloudWatch, and Amazon SNS for monitoring and reporting, for example, system logs or some potential errors. And this Amazon SNS, it's a quite useful feature actually, because I configure Amazon SNS to send me some warning emails when some Lambda function fails. Okay, next part of this system is data warehouse. As you can see, the transformed data sets are loaded into the Postgres data warehouse hosted on AWS RDS, and using a star schema design with some dimension and fact tables. And here you can see my ER diagram of this simple data warehouse, but still. Basically, I have created 2 fact tables, fact prices and fact metrics, and 3 dimension tables, right? Dim country, dim product, and dim date over here. Okay, I choose this particular star schema because after some hypothetical, of course, interviews with stakeholders, we established that 3 main dimensions for data aggregations are country, date, and product. And why 2, not 1 fact table? Well, the 2 fact tables were separated because they represent different business processes and contain measures with different granularity, structure, and source system. And first fact prices stores commodity price data from World Bank, while this fact metrics table stores production, consumption, import, export, and some population also metrics from FAO Stat and World Bank. Okay, let's go back to project architecture diagram. Here we have some final product from some data serving. In this case, the final data product is an interactive Tableau dashboard. Here, and this dashboard enables analysis of global food trends, prices, like over here on this line chart, and some indicators, some KPIs, like here, for example, global consumption, production in some particular year. And of course, data warehouse can be a final data product as well. For example, analysts can query model data to get some additional insights from it. Okay. Last part of this system architecture is some undercurrents. Okay, I take under consideration security, data quality, CI/CD pipelines, monitoring, scalability, and fault tolerance. Let's start with security. Well, credentials and configurations are managed using AWS environment variables and EAM roles, right? I can connect to RDS data warehouse, for example, using credentials written in .env file, which is of course included in gitignore file. Then data quality. I implemented automated validation logic and unit tests. As you can see here, using GitHub Actions, I can conduct automatically some data validation. So it's also a Lambda function which validates data with Panda script, as far as I remember, after data are stored in transform zone. And additionally, GitHub Action workflow conduct automatically unit tests after some Git push, for example, or pull requests made by me. Yes, so full automatization of data validation and unit tests. We have also, as I mentioned before, some monitoring. So I use CloudWatch for monitoring and logs. I will show you later how this monitoring dashboard looks like. And what about scalability? Well, this is serverless architecture, so it enables scalable processing without some infrastructure management. And last undercurrent is fault tolerance. And well, this row and transform data separation, it improves recovery and some debugging capabilities. Okay, so finally, let's move to implementation details and check out my repository and some code samples. Okay, so implementation and some engineering challenges I had to deal with in this project. Let's start with well, brief present of repository structure of this project. The repository was organized to separate the main ETL stages and supporting components into modular folders, and that way making the pipeline easier to maintain, test, and extend. As you can see over here, this is my GitHub repository of this project, and we have several folders over here which we will discuss. So first one is GitHub and workflows folder. This folder contains GitHub Actions workflows, responsible for automated unit testing and data validation as a part of CI processes. This is basically a YAML file with some triggers and jobs. And this is run test, and then this is validate transfer data workflow, also in YAML file. Then we have data folder. This is basically data folder contains local data sets used for development and testing, including raw data, transform data sets, and some additional reference files. So we have resources over here with CSV, with continents CSV, and we have transform CSV files for dimension and fact tables. Then we have diagram folder, and these folders, I already show it to you. This folder stores the architecture diagram and warehouse schema diagram used for documentation and system design. Next, a very important folder is Lambda layer, and we have some zip file over here. And this directory contains now the reusable AWS Lambda layers used to package shared dependencies and helper models across multiple Lambda functions I use in this project. And then we have some source code, so src file. This is where all the source code, Python code, and SQL code is loaded. So this folder contains the core ETL pipeline logic and is divided into separate modules. Extraction over here for ingestion scripts, transformation, over here for data processing logic, and also load data folder. Moment. For warehouse loading scripts, and additionally data warehouse folder, which has some SQL schema definitions, so data warehouse definitions over here, and some helpers for reusable utility models. And last folder in this area is validation with validation Lambda code over here. Then we have tests, which of course this folder contains unit tests for transformation logic and helper models and loading functionality. Okay, so this is basically the repository architecture or structure. And as I mentioned before, one of the main design goals was modularity and separation of the responsibilities. So instead of creating a single monolithic pipeline script, I organize the project into independent layers responsible for ingestion, transformation, loading, validation, testing, and infrastructure support. And the structure makes the project easier to debug, maintain, and extend with some new data sets, OTL stages in the future. And very important part is that this repository structure reflects the architecture of this system. And this is like my tip to you if you are a beginner in data engineering. Before you start design data architecture or write code, well, you should stop for a moment and think how your repository should look like, because once your project will start getting bigger and bigger, and in data engineering it probably will, clear repository structure will help you manage increasing project volume. And of course it's also useful when you have to come back to your project after some time and remember what this project was about. So this is repository structure. Okay, next let's jump into cloud environment of this system. Okay, well, next thing I would like to share with you is cloud environment. Well, as you probably remember, I used to create this system with different AWS services, which I show you on this architectural diagram before, but here I will show you just 3 of them: S3 for storage, EventBridge for scheduling, and Lambda functions for computations. This is AWS Management Console. Of course, there are also different, more effective ways to communicate and design and maintain your cloud infrastructure, like CLI, or even tools like Terraform for infrastructure as code approach. But for presentation purposes, I will use this management console. Okay, so let's start with S3. Well, this service serves as a central storage layer of the solution and acts as a simple data lake. And since S3 is an object storage service and does not provide a true folder hierarchy, I use a single bucket. Basically, I use different single buckets for every project I made. And inside this bucket, we have different prefixes representing some logical, layers, such as row over here with row files, and transformed with transform data CSV files. To organize the data throughout the pipeline. And as you can see here, this bucket also contains 2 additional dedicated prefixes, which are Lambda layer, with project 1 common layers zip file. This is like reusable Lambda dependencies. And we have also resources prefix over here, and this prefix contains dataset called N49 continent CSV, which I use as a mapping file used during the data transformations for continent granularity aggregations. Okay, so this is storage layer based on S3 bucket. Then we have EventBridge, and I have like 12 scheduled rules here. So basically we create rules in EventBridge, and well, Amazon EventBridge here is used as the scheduling layer of this pipeline, because each Lambda function has its own EventBridge rule, as you can see here. With a cron expression that determines, when the function should execute, right? For example, let's check one of these rules. For example, this one, monthly extract second day. And as you can see here, we have cron expression, which means that the extraction Lambda runs at 9 a.m. on the second day of the month, on every month, and similar schedules are configured for the downstream transformation and some loading functions. And based on this cron, we have here next 10 trigger dates for this particular Lambda function, which extract data from data source and load it into the S3 row zone. And well, I selected the cron-based approach because the source datasets are updated relatively infrequently, typically monthly or yearly. And at the same time, I'm aware that this is not like a true orchestration solution, because EventBridge schedules tasks independently and does not support or manage orchestration features like dependencies, retries, or execution order between pipeline stages. Probably, for the production grade implementation, I would consider orchestration tools such as Apache Airflow or AWS Step Function, which, by the way, I use in my next projects. And this tools, these frameworks, they provide workflow management, dependency tracking, monitoring, and, for example, failure recovery. Okay, so this is Amazon EventBridge and scheduled rules for each individual Lambda functions. And then we have this computing service in this project, so Lambda functions. I have like 19 functions over here. Part of them is for this particular project. As I mentioned before, AWS Lambda is a serverless compute service that allows to execute code without provisioning or managing servers or virtual machines like EC2 instances, for example, right? Okay, so I will show you different functionalities of these functions and how to establish and run them. Basically, each individual ETL stages, such as ingestion, transformation, validation, were implemented as separate Lambda functions. And as you can see here, we have Lambda function for downloading data from data sources to S3 row. We have different functions for loading data from transform zone into data warehouse. These are functions from another project, but here we have transformation lambdas for transforming raw data and loading them into transformed zone. Okay, and each function executes independently in response to or EventBridge cron rule or a trigger, which I show you in a moment. And each function processes a specific part of this pipeline, and well, automatically scales based on workload. Okay, so a few things about Lambda service and using this service in my project. First thing I would like to show you is like deployment model. Let's check, for example, transform dim country function. A moment. Source code is loading. So every Lambda function has some layers, some triggers, of course code, and some configuration. What about deployment model? Once again, AWS Lambda functions are typically deployed as zip packages containing Python code, dependencies, some helper models if you have some, and some configuration files required during execution. And how this deployment model looks like in practice. This is functionality called layer. And I separated a shared functionality into AWS Lambda layers and prepared zip deployment packages for each individual ETL functions. And this package is loaded into S3 bucket. So this is this zip file stored here in S3. And Lambda layers are reusable dependency packages attached to functions during deployment. And in this project, they were used to share common helper models and Python libraries across multiple ETL stages. So if we see this layer, we have one layer here, and this name of this layer is project one common layer over here, and it's basically this file here. Okay, next functionality I would like to show you is triggers. Basically, I have two kinds of triggers used in this project. Let's come back to Lambda functions. Okay. And let's check some triggers in my functions. Let's see, for example, download to S3 row. As you can see here, we have EventBridge trigger, and basically each Lambda function also requires, a trigger defining when the function should execute. And basically, depending on the use case, Lambda functions in AWS can be triggered by different events, like, for example, this EventBridge. For example, S3 event, like loading file into some S3 destination. And I use this approach as well. I can show you here. For example, transform dim country. Sorry, dim country over here. As you can see, there's a different kind of trigger here. But you can use another different triggers to run your Lambda functions. For example, API gateway requests, some SNS notifications, or some other AWS services, actions. So in this project, as I mentioned before, I use EventBridge cron schedules, but also this S3 event triggers. So basically, every time some new file occurs in S3 destination, right? You can check details. Every time some object is created in this destination, this function is triggered, and automatic transformations starts. Okay, so two kinds of triggers to sum up. Another functionality I would like to show you is some general configuration, which you have to configure when you want to use Lambda as a compute service. So we have configuration and some general configuration. Basically, we have three runtime configuration parameters, basic, and these are timeout, memory, and something called ephemeral storage. Okay, so timeout, well, it defines the maximum execution time before the function is terminated. Next, we have this memory allocation, and it affects both available RAM and CPU power. So increasing memory can improve processing performance. And this ephemeral storage over here, I check AWS documentation, and basically this parameter provides some temporary disk space available during execution, during every Lambda function execution, which is useful for intermediate file processing, for example. And to sum up, these parameters were adjusted depending on the workload size and transformation complexity of each ETL stage, right? And how do you do it? How do you establish these parameters? Well, I did it by experimenting with different parameters configuration. So general configuration, triggers, layers, and last functionality, or last thing I would like to show you is environment variables, because I use them in functions code, so I had to define them somewhere, and these are environment variables for this particular transform dim country Lambda function. So I use, this Lambda environment variables over here. To store additional configuration parameters such as S3 bucket, name, prefixes, and, for example, I don't know, database connection settings. And this approach, it allows me to separate configuration from application code, making these functions once again easier to maintain, debug, and deploy across different environments. And one last component of the cloud architecture worth mentioning is Amazon RDS deployment. So let's go back to Management Console and let's check Amazon RDS. And this Amazon RDS, hosts the PostgreSQL data warehouse. And after creating this RDS instance, I use a SQL schema script to build, the star schema model consisting of fact and this dimension tables. I will show you this SQL script later. But like two things about quite important things about database or RDS deployment. In general, here is database instance. In general, this database is deployed inside something what is called VPC, so Virtual Private Cloud. And in simple words, it's like a logically isolated private network within AWS resources, where you can, securely deploy and manage different cloud resources such as database, servers, or different kind of applications. So I have here one database instance, free tier instance, because it's based on free tier. And as you can see here in this section, this database instance is protected by security groups. And these security groups, they act as stateful virtual firewalls attached directly to this instance. And because these security groups are stateful, so you need to establish like inbound and outbound rules over here and over here. But once an inbound connection is or traffic is allowed, the response traffic is automatically permitted, right? And in this project, I configured the inbound rules, as you can see here. These are inbound rules. So I configured these inbound rules to allow PostgreSQL connections only from my public IP address. I can show it to you because it changes all the time. While the outbound rule traffic is over here, is unrestricted. This reduces, unauthorized access to the warehouse. And last one thing, it's also worth noting the difference between the security groups and some other networking components in the AWS. For example, subnets are used to logically separate resources within the VPC, while there's something called network ACLs, so access control lists, but they provide stateless traffic filtering at the subnet level. So, and the security groups, which I use over here, on the other hand, they control access directly to individual AWS resources, like in this case, this particular RDS instance, database instance on which I have created this data warehouse. Okay. So just quick mention about RDS and how to deploy it on AWS. Okay, so that was a quick overview of the cloud infrastructure in this project. As you probably know, Lambda functions, they also, of course, need some code to execute transformations or loading or extracting data from external data sources. So now let's move to the code part. This system, consists of over 15 different Python scripts. So of course, I won't show you all of them because it would, take hours to analyze all code. If you are interested, you can check my, GitHub repository. But I will show you just one Python script for each task within the ETL pipeline. So one for ingestion, one for transformations, and one for loading data into the data warehouse. So we can jump into my GitHub repository, and there's a source code, extraction, and download to S3 row Python file. Let's maybe zoom in a little bit. Okay, so this is ingestion script. This script represents, this ingestion layer of the pipeline. And in general, what this script does, well, the script downloads data from two main source systems, FAO Stat and World Bank. Once again, FAO Stat provides food production and trade and consumption data sets, while the World Bank provides pricing and also population data. And the output of this step is a set of raw files stored in Amazon S3 under the configured row prefix over here. And well, one thing to remember that at this stage the goal is not to clean and reshape data, but to preserve the original source files in the row layer. So let's analyze the key parts of the code. Okay, first, of course, we have some library imports. So I import Boto3, which is a official SDK for Python. Some requests, bytes.io, and so on. And then we have the definition of the function over here. And this is because this script is designed to run as a AWS Lambda function, and this Lambda handler, let's start with it, is like a standard Lambda entry point, and we have two parameters here, event and context over here. These parameters are automatically provided by the AWS Lambda runtime. The event parameter contains information about the trigger that invoked the function, such as this EventBridge schedule or this S3 object creation event. And while this context parameter provides runtime metadata about the Lambda execution environment. But in this particular function, The event payload is not explicitly processed because the required configuration is read from environment variables, as I showed you before, and some predefined S3 locations. Of course, we have some doc strings over here with function definition, environment variables, and returns. And this function returns a Python dictionary if all downloads were successful. So the status is then successful. Success, actually, sorry. Then we have some data sources. So data sources variable over here. So I keep source URLs in this Python dictionary, where each key represents a logical, dataset name, like file.production, file.export/import, file.consumption, and World Bank prices. And the values are these URLs, right, for each data set. And this makes the ingestion logic easier to extend. Yes, because if you want to add some other source, you can add another entry here without changing the main download loop over here. Okay. Then we have these three variables. These are like S3 client and environment variables over here. So the script uses Boto3 to communicate with S3. So we need to establish Boto3 client for S3 service, and then the bucket name and the row prefix over here are read from environment variables instead of being hard-coded. As I showed you before, these environment variables are loaded here into each Lambda configuration. And this once again makes this function more secure and easier to deploy across different environments. Then we have this download loop. Let's start this for file name, URL, and data source items. So basically this function loops through all configured sources, configured here, right? Sends HTTP requests and downloads the files. And one thing I would like to point you, this is this parameter stream. It is set to true. Why? To enable the streaming downloads, which helps handle larger files more effectively by avoiding loading the entire response into memory at once. I will zoom in once more. Okay. Then we have this if statement. So if response status code is equals to 100, and this part of the code checks whether the HTTP request was successful, and status code to 100 means that the source files were downloaded correctly. One thing to show you, this downloaded file content is then wrapped using bytes.io, which creates some kind of in-memory binary buffer, behaving like a file object. And this bytes.io comes from Python's built-in IO library, which I import here. And it is, commonly used when working with binary data such as zip files or Excel files or some images without saving them temporarily on disk. And particularly in this project, it allows the pipeline to process downloaded files directly in memory and upload them to S3 efficiently inside AWS Lambda, where in AWS Lambda local storage is limited and temporary. Okay. Then we have over here. This part of code, this line of code, because the pipeline handles different input formats like zip files and Excel files. I use this extension over here. This is very common in real data engineering projects because external sources rarely provide data in one consistent format. And then another code line, put object into S3 bucket. After downloading each file, the script writes it directly to S3 row layer, and this key parameter here, makes these files well stored using clear, consistent, names such as, for example, file stat production with some zip, for example, extension, or World Bank prices with XLSX extension over here. And last part of this code over here is made because of the special handling for World Bank population data. Why? Because World Bank population data set is downloaded as a zip archive, and inside this zip file the script extracts only the actual CSV data over here, right, and skips some metadata files, and this part of the code keeps the row S3 layer cleaner and avoids strong unnecessary files. And of course, last but not least, we have error handling in this function over here. So if the download fails, the Lambda function raises an exception and a statement: fail to download, for example, population data in this particular case. And this is important because the pipeline should fail clearly instead of, I don't know, some silently producing some incomplete data, right? And in AWS, such failures can be tracked in CloudWatch logs, for example, and can be connected to some alerting mechanisms, for example, with Amazon SNS mechanism, which I show you, which I mentioned actually before. Okay, so this is Python code for this first extract script. In summary, this ingestion script integrates multiple external data sources, World Bank and FAO stat, supports different file formats like zip files, Excel files, uses environment variables for configuration, and fails explicitly when a source download is unsuccessful. And this design gives the pipeline a clear starting point. Raw data is preserved in S3, and later stages can be focused can focus only on transformation, validation, and warehouse loading. So now let's move to one example of transformation script. Okay, so I choose to show you transform fact prices transformation script over here. Okay, this script represents one of the transformation steps in this ETL pipeline. Its goal is to transform raw World Bank monthly commodity price data into a clean analytical fact table called fact prices. Basically, the script reads the raw Excel file from S3 row zone, selects some relevant food products, then reshapes the data set, calculates some new features, some price related metrics, joins dimension tables, and eventually saves the final fact table back to the S3 transformed zone. Before I jump into the code explanation, let's check how this raw World Bank dataset looks like. It's over here, and as you can see, there's a lot to do. For example, we need to standardize feature names, remove some white spaces from it, remove some unnecessary rows as well, and since there's a lot of different products here in this data set, so we need to choose features that we need in this case. So this is how this raw data World Bank data set looks like. Okay. Okay, so transform fact prices Python script. Of course, first we have some library imports. Well, in this case, I use pandas data frame. Pandas library to do some transformations. Then we have once again Lambda function definition with Lambda handler with event and context parameters. Then we have once again some docstring, some environment, once again some environment variables configuration over here, and then some file keys definitions or variables over here, because we need them in further transformations. Once again, we establish an S3 client, bot-free client, to communicate with AWS S3 service, because we need to take from raw data from S3 row zone, and then after transformation we need to store that data or load the data into S3 transformed zone. Okay, what next? This part of the code what is all about? Well, the data, the source data, well, is stored as, in S3 as Excel file downloaded from the workbench, and the script, reads it directly from the raw layer without using some local files. Then over here in this line of code, I create some pandas data frame object. And this pandas library function parses, the virtual Excel file and select the specific sheet and indicates that the table headers, so like column names, are located in fifth row. And since indexing starts at 0, so header equals 4, means that the first 4 lines of text in the sheet are skipped, right? Because over here in the row data set we have these 4 first rows which we have to remove. Okay, then we have some cleaning and renaming columns in this 3 line of code. Because the row exit file contains additional formatting and non-standard headers. So the first transformation step is like basic cleaning, removing unnecessary rows, renaming the date column over here, and stripping white spaces from column names. This line of the code do that, because we have over here white spaces in column names. Okay, next part of this script. And since the workbench file, this file contains many different commodities, but this project focuses only on selected food products. So to choose this selected food products, I use this product mapping dictionary to select relevant columns and standardize product names so they match the product dimension table, which was also created by some transformations. So we have this renaming, like for example this wheat US something, we changed to wheat. Rice Thai 5%, it's some kind of rice, we changed this name into rice column name. Okay, next and like very important part, transformation. It's reshaping and melting over here. This 5 line of code, and this is like the most important transformation in the script. Here in this first line, I'm calling the melt method on the filtered data frame, which I established here earlier. I do that to to unpivot the data set, converting product columns into rows. And why to do that? Well, because the raw workbench file is, as you can see here, in a wide format, where each product is stored as a separate column, right? We have coffee, tea, palm oil, maize. So each product, well, one product, one column. And this format, this wide format, is readable for humans, but it is not ideal for analytical modeling or loading data into the fact table. And this melt operation converts product columns into rows, and this creates normalized long format where each row represents one product price for 1 month. 1 month, yes, because the date granularity here is month. Okay, so we have in this melt method 3 very important parameters. First one is ID vars over here, and ID vars defines the column that should remain unchanged during the melt operation and act as some kind of identifier for each row. Then we have var name parameter, and this var name specifies the name of the new column. In this case, it's going to be product name, and this var name, this product name, will store the original column names converted into row values. Yeah, and the last parameter, value name, price USD per ton, and this value name defines the name of the new column that will contain the actual values extracted from the original wide format columns. And well, why this converted long format is better here? Well, long format is better for this pipeline because the final warehouse model uses fact and dimension tables, and each row in fact table, in fact prices table, should represent some one measurable business event. In this case is the price of one product in one time period. And this structure is easier to join with the dimension product and dimension date, and it's easier to query in SQL, and probably it's also more flexible for BI tools like Tableau, which I use as a final data product. Okay, another transformation I made over here. These are transformations on date. Because the source uses a compact date format, such as, for example, here. So, for example, 1960 M01, right? And I convert it into a proper date object and extract year and month over here values. And these fields are later used to join the price record with date dimensions. Okay. Next transformations are some feature engineering over here. So I have created 3 new features based on existing ones. The first one, average annual price over here. This calculates the average annual price for each product. Second one calculates the month-over-month percentage price change. And the last one, price annual change percentage. This line of the code calculates the annual price change percentage based on average annual prices. And these three metrics, new metrics, make the final data set more useful for business analytics, because users can compare price levels and, for example, price dynamics over time. Okay, then we have joining dimension tables. And to do that, we need to load dimensions table from S3. And this block of code uses bot3 client, which we defined before, to fetch 2-dimension files, products and dates, from S3 bucket. As you can see here, we also use these keys, which we define also file keys, which we defined before over here. Okay, and then the last 2 lines of this section. The code then reads their raw byte streams, bytes IO, into memory using this bytes IO, and loads them directly into the pandas data frames as dim product and dim date, without writing anything on disk. And after preparing the price data, which was all these transformations I showed you before, the script joins this data with product and date dimension tables. And this is the part over here where the data set becomes aligned with star schema warehouse model I have created. And instead of storing product names and raw dates directly in the fact table, which is wrong, I store foraging keys, product ID here and date ID over here. Okay, and after joining this transform price data with dim product and dim date data sets, we can create a final fact table. So the final table contains only analytical measures and foraging keys to dimension tables. And why? Because it keeps the fact table clean, compact, and optimized for reporting. One last thing I would like to show you, that I also here I generated a technical primary key called price ID, because every table needs to have some primary key. And one important thing about creating this primary key here before generating the price ID column, I reset over here the data frame index. Why? To ensure that the surrogate key values are, sequential and start from 1, and they are not, affected by any previous sorting, filtering, or transformation operations that may have, modified the original index. Okay. And finally, the transformed fact table is saved as a CSV file and stored, in S3 transformed zone. And from there, it can be, validated and later loaded into the PostgreSQL data where saving to CSV and uploading this transformed dataset into S3 transformed zone. Okay, so in summary, the script transforms raw World Bank commodity price data into an analytical fact table. The script, as you could see, cleans the source file, standardize some product names, extracts date attributes, calculates some new features like price metrics, then joins product and date dimensions, and saves the final fact prices table into the transform S3 layer. And the important part of this transformation is melt operation, which converts, as I said, the source data from the wide format into the long format, and it makes the dataset compatible with the warehouse star schema, where each row represents one product per for 1 month. And in my opinion, this is like the most important stage of this pipeline. I mean transformations, because transforming raw data into some useful business knowledge, or transforming raw data into transformed data which can be used to extract business knowledge from it, is the point where a data engineer can create the most value for the organization. Okay, that was the long one, and we have one script to go. So let's check one loading script. Okay, let's, for example, take under consideration loading product. Okay, well, this script represents the load stage of the last stage of the ETL pipeline. As you probably know, its responsibility is to take a transform dimension table from S3 and load it into the PostgreSQL data warehouse, which is hosted on Amazon RDS. And of course, cloud infrastructure was created before, and data warehouse model was predefined with these DDL, this one, DDL script. Okay, so let's check for a moment this SQL script before we jump into the details of loading data into data warehouse. In in this particular SQL script, first I create 3 dimension tables. So dim date, dim product, and dim country. And then 2 fact tables that form a core of a warehouse star schema. So here is fact metrics table, and here is fact prices table. Of course, here the foraging keys relationships connect the fact tables to the dimensions, and ensuring referential integrity and enabling analytical queries based on product, country, and time. So also here we have foraging keys, and in every dimension table I have also created primary keys, primary here and primary key here. So country ID, product ID, and of course date ID. And well, after defining the tables, I have created some indexes over here on the most frequently queried foraging keys columns, to improve join and filtering performance. And finally, the last part of the script here, I add table and column comments to document the warehouse model directly inside the PostgreSQL, and making it easier to future users and developers to understand the purpose of each table and metrics. So to sum up this SQL script, in general, fact tables store business metrics, like here production, consumption, import, export, population, and this features which I show you, which I created in the transformation part of the pipeline over here, like price, average annual price, price changes, percentage, and so on. And while dimension tables provide some descriptive context such as product dates and country. Okay, and this structure, star schema, simplifies SQL analysis and as I said before, improves dashboard performance. Okay, so this is data warehouse creation SQL script, and now let's go back to loading product over here, and let's analyze what's in this Python loading script. Okay, well, first of all, what this script does, the script loads dim product CSV file from transform S3 layer into this table dim product in PostgreSQL, and this is the final step that makes the transform data available for SQL queries. Okay, so first, as usual, some library imports. I import also Psycop PG2 library for database connection, and as you can see here, I have used for the first time my helper functions over here. So from SRC helpers, this is here, and some particular script like S3 utils or DB utils, I import some predefined functions, right? Like read CSV from S3 or get DB connection. I will show you in a moment this helper scripts. Why did I do that? To reduce code the duplication. I extracted reusable functionality into helper modules such as S3 utils right here and DB utils. And these models centralize common operations like reading files from S3 or connecting to PostgreSQL and making the ETL scripts cleaner and easier to extend. So this is my helper. As you can see here, this is like a short and simple script where I define function get DB connection, and for example, this helpers in this script, I define 3 functions for reading or CSV from S3, reading Excel from S3, or writing some CSV files to S3. And then I can use those helper functions in many different, for example, load scripts. Loading product. And how it works? Well, this works because this src and helpers are treated as a Python packages models, and this file here init.py, there's no code over here, but this file marks folders as some importable Python packages. Although from Python version, I think 3.3, they are not always they are not always strictly required, as far as I can tell. And one thing to remember, since it's a Lambda deployment, you must remember that this project structure, so also this init files, init scripts must also be included in the zip package, so that these modules are available at Lambda runtime. Okay, so this is quite cool to use these functions more than once in many different load scripts. Okay, but then once again we define Lambda handler with these 2 parameters, docstring. Then we have some, once again, environment variables like in transformation script or this extraction script, right? So the script, reads the S3 bucket name and transform prefixes from environment variables. And then this part of the code, the script, in this part of the code, the script reads the already transformed dim product CSV file from S3. And this is the moment I use this first helper function, read CSV from S3, right here. I import it, and here is the moment I can use this function. So this way, I keep the loading script clean and avoid duplicating, S3 reading logic across multiple load scripts. Okay, and then we have to establish connection with the Postgres RDS database. So this part of the code so we establish a connection to the Postgres data warehouse. Cursor is like database cursor. object created from the PostgreSQL connection. In this moment, we use this another helper function, getDB connection, right? And this cursor, it comes, from PsychoPG2, and it is used to execute SQL commands against the database. So to sum up, the connection manages the database session, while the cursor is used to send SQL operations within this particular session. And once again, as I said, this database connection logic is separated into DB utils. So credentials and connection parameters that are, handled centrally. This is why we use this function. Okay, what next? Then we truncate table before inserting new data in it. So this line of code with cursor execute, and then we have this SQL statement. Truncate table dim product restart identity. Why go? Before loading new data, the script truncates the target table. It's okay in this project because dim product is a small reference dimension, so a full refresh approach is simple and reliable. And this restart identity part, it restarts the table identity sequence, which helps keep the load deterministic and consistent between runs. Okay, what else? Then we have prepare data for copying. Yeah. So in this part, basically, the data frame, pandas data frame, is converted into a in-memory CSV buffer using this string IO. And why? Because this avoids writing temporary files to disk and prepares the data for PostgreSQL like bulk loading. Why to do that? Well, it is needed because PostgreSQL copy expects file-like input, right? And strings IO lets us provide that input without saving a temporary CSV file on disk. And since this is like serverless Lambda approach, this approach fits well with this Lambda serverless architecture, because Lambda has limited temporary storage, so processing data in memory is often simpler and cleaner. And this part, buffer seek 0, moves the read position back to the beginning of the buffer before PostgreSQL reads from it. So this is like preparing data for copy. Okay, and then we have loading data using copy over here. And why to use this copy expert method? Well, instead of inserting rows one by one, the script uses this Postgres copy command through copy expert, and this is much faster and more efficient for loading tabular data into Postgres, especially as data sets grow. So we use this method, copy expert. And then almost last part of the script, this part. after data is loaded, the transaction is committed, and the database connection needs to be closed. And closing connection is, especially important in Lambda-based pipelines, because open database connections can, accumulate and cause some open operational issues. So we have to close cursor and close connection. And okay, so this is loading script. To sum up, this script shows the load layer of this pipeline. It reads transform CSV file from S3 transform zone, connects to the PostgreSQL warehouse, truncates the target dimension table over here, and loads the data using Postgres copy command, and then some cleaning and closing connection. Well, the fun and important part is this script use the helper models over here and here, and this use of helper models makes the code cleaner and easier to maintain. And why this bulk approach to loading data is more efficient than row by row insert. Okay. So to sum up, I show you one extraction script, one transformation script, and one loading script. And of course, there's a lot of different other models and scripts in this solution, and I won't dive into the details of all of them. If you are interested about details, you can check them at my GitHub repository. I already showed you this SQL warehouse schema script and some helpers. Now let's just make like a very quick overview of the two other modules. So validation script and CI/CD workflow. Here is in helpers. Here is a validation script. I won't analyze all code, of course, because it's quite a lot of different functions here. In general, validation scripts are responsible for checking the quality and consistency of transformed data set before they are loaded into the warehouse. And this validation module is divided into basically 1, 2, and 3. Yeah, 3 logical sections. So the first one is generic validation functions. The first section contains just generic validation functions that can be reused across different data sets to verify, for example, schema consistency, some null checks, uniqueness, for example here, value ranges, row counts, duplicates, and so on. So basic data quality checks. Then on this second section, well, I define some dataset specific validation rules for each dimension and each fact table. So for example, for dim country, we have different checks. For dim date, we have other different checks, and so on, right? For dim product, we check schema, nulls, uniqueness, row count, duplicates, and so finally, over here, third section, this is like main validation runner, which automatically is loading all transform data sets and is executing appropriate validation functions before data is loaded into the warehouse. And in general, this helps reduce the risk of loading incorrect or incomplete data into downstream analytical layer. So this was validation script, and let's just check last script. So CI/CD workflow, we have GitHub folder here, and we have two workflows: run tests, YAML file, and validates transformed YAML file. Let's check, for example, run tests, YAML file. Okay, so I implemented a CI/CD workflow using GitHub Actions in this case to automate unit testing or this data validation. And the workflows, those two workflows, they execute automatically on push or pull request. So here, pull request, push, the same here. Push or pull request. So every time I do some git push action into the development branch, or I conduct some pull request. These two workflows, they start unit testing or data validation. And well, it helps detecting transformation and validation issues earlier in the development process. So CI CD two workflows, and correct me if I'm wrong, but this approach, like CI approach, together with the system modularity, and for example using helper models or helper functions, well, it introduces some level production-oriented engineering practice, well, my honest opinion. And speaking about engineering, let's do very quickly so quick overview of some engineering challenges in this project, just really quickly. So first challenge was schema consistency. The problem was, well, different dataset had inconsistent schema and formats, and my solution to that was the standardized transformation layer with different transformation script using pandas normalization logic. Second challenge was data validation. The problem was the risk of loading, invalid or incomplete data sets, as I mentioned before. And the solution, I just showed you my solution. So I implemented validation scripts and automated, testing workflows in GitHub Actions. Well, third challenge, maintainability. Well, the problem was that the pipeline complexity increases very quickly during this project, and simple solution like modular architecture. So different models for ingestion, different for transformation, loading, different for helpers, and different for validation. Okay, and maybe last challenge. Well, I think it's like a challenge in every data project. So cost optimization. and it was like a problem also personally for me, because I didn't want to pay like hundreds of dollars for running EC2 instances, for example. So the problem was need for low-cost cloud architecture, and the solution was like selected fully serverless AWS services like Lambda for computing, S3 for storage, and EventBridge for event scheduling, right? So for above challenges was like design challenges, but I had also in this project a lot of practical problems, especially during the code creation. And one of the main problem was handling some inconsistent source data formats were coming from external data sets, like for example this World Bank commodity pricing data I showed you before. And quick tip how I solve these problems, of course, by experimenting and making mistakes, like a lot of different mistakes. And finally, I introduced a dedicated transformation layer using pandas in this case, because it wasn't some big data solution. So pandas was more than enough. Generally, I implemented schema standardizations, as you could see, column cleaning, product mapping dictionaries, date normalization, and this melt transformation, converting dataset from wide to long format. And after these changes, after these transformations, the transformed datasets become fully compatible with the Postgres warehouse model and Tableau dashboard. Okay, I think it's enough about code. As I mentioned before, there's a lot more code here if you want to check it. And if you have any questions about that, please do not hesitate to ask them. And you can check this code, this additional extra transformations or helpers over here, or loaders at my GitHub repository. Okay, now let's move to the final and last part of this video, so data product demo. Okay, welcome to the last part of this video, so data product demo. And in this section, I will show you the how final data products work. And to do that, I will do two things. First, I will query some data from data warehouse, and then I will show you in brief this final Tableau dashboard I have created. And well, I'm not going to to create some sophisticated advanced queries to analyze results and make some big business very important conclusions, because this is not the purpose of this video. I just simply want to show you that the data warehouse works, and there are cleaned and transformed data inside this data warehouse. Okay, so let's start. I will use VS Code for SQL queries, and to do that, first I need to connect to the data warehouse with VS Code, and then create some files, and then create some queries. Okay, so this is my VS Code. I have installed previously extension here, Postgres extension, and I have two servers over here. Of course, I previously also configured connection. So to connect to the server, you need to have and write here server name. You need to have username, password, database name, and so on. So first, let's try to connect with this RDS database. Yeah. We have a connection. So we have here two databases. And in this database, we have schemas, public schemas, so tables. And as you can see here, we have 3-dimension tables and 2 fact tables. So this is our simple data warehouse. Okay, let's go back to Explorer, and then let's create some SQL file. Let's name it, I don't know, sample queries. Okay, and we need to connect it to the Postgres with this food trends instance database, actually. Yeah, so we are connected. So now we can create and run some queries to check what do we have in this simple data warehouse. Okay. Okay. So first simple query, I don't know, against, let's say, prices table. So select from prices, and let's select, for example, price ID. Okay, product ID, maybe simply price, and let's say average annual price, and then let's just limit results to 10, for example. Okay, so 4 features: price ID, product ID, price USD in dollars per ton, and average annual price for each product. Let's run this query, and here we have results. So as you can see here, we have price ID. It's like primary key for this table. Then we have product ID. Then we have price in US dollars per ton, and how it changed month to month, because the granularity is January, February, March, and so on. Yeah, so every row is different month. And the last feature is average annual price, and since this price is annual, so it's the same for whole year. If we change this limit, for example, to 20, I don't know, 5 maybe, then we can see that this, after 12 months, this annual average annual price changes, right? And after another year, and after another 12 months, once again, this average annual price changes. All right, so this is like I know this is like a simple query, but it shows how the warehouse stores analytical metrics. In this case, in fact prices metrics, such as monthly prices, and over here, and annual average prices. And we can see also the data inside this table, right? And they are transformed. Okay, let's create another query, this time maybe a little bit more advanced. Let's join some tables together to check if the star schema is actually working. So select from fact prices. Let's alias this this table F, and let's join maybe dimension products table on product ID. Yeah, and let's join another maybe not dim countries but dim date, and it's gonna be alias D and on date ID, right? Because this is like primary and origin key. Okay, so we have joining here. And now let's select some features, like for example, year from dim date table. Here add an alias the change here the dim date. Okay, so here well, maybe some product name and I don't know, maybe some average or price per ton, but let's make it average, for example. And maybe as average price. Okay, so we just have to, and let's group by the first year maybe, and then product name. Okay, and let's order by year, and then maybe average price. Descending, that's okay. Okay, let's check if this query works. Doesn't. And in product does not relation in product. My numbers in product. Okay, one simple mistake. And we can round this average price to 2 decimal points, for example. Once again, run it, and no, okay. Okay, so this query basically joins fact prices table with the dimension product and dimension date. So 2 dimensions. So as we can see, well, the star schema works, and it calculates average yearly prices for each product, so rice, soya, wheat, maize, and so on for each particular year. And this, simply demonstrates how the star schema model supports analytical queries using business-friendly dimensions instead of row IDs. Okay. Now let's move to third query, last one. Okay, and this time maybe a query which shows some more advanced analytical aggregation. And to do that, let's copy the previous query, because we still need joining with dim product and dim date. Okay, so select dim year, product name once again, that's okay. Let's remove this one from track prices, F dim product, joining on product ID, joining on date ID with dim date. That's also okay. Grouping and ordering, well, maybe later. Okay, and let's have 3 different statistical aggregations. So for example, average, but this time let's say for price month change, okay, as average monthly change percentage. Let's then maybe let's create maximum of price max as max price, and maybe minimum, once again, price as minimum price. That's okay. Let's round it to 2 decimal points. Once again, 2 decimal points, okay. So year, product name, and 3 aggregation functions, average, mix, maximum, and minimum. Okay, from fact prices as alias F, joining with dim product, on product ID, joining with dim date, on date ID. Now, well, let's group by year and maybe product name, that's okay, but let's order by, for example, this average monthly change percentage. That's also okay. And one more thing to go, having this average can't use alias, so having that for example is not null. Okay, let's check if it's working. 1000 line 4. In terms of the query round, okay. Oh, there's like here. Now if it's working. Well, yeah, it's working. Okay, so as I mentioned, this query, this last one query performs a more advanced analytical aggregation. Once again, I combine the fact prices table with two-dimension tables, dim product and dim date. But this time I calculate average monthly price change over here, maximum price and minimum price, product price, and I group it by year and product once again, and I use this here, this having clause to exclude groups with missing monthly change calculations and ensure that only valid price and statistics are returned. And strictly speaking, Postgres probably ignores null values in average calculations. So this having clause acts as a additional safeguard to exclude groups without any valid monthly change observations. Okay, and what about results of this last query? Look at this part, for example, here. Well, basically this query reveals that there are periods of some unusual high price changes across different commodities. For example, this one here, rice product, experienced the highest average monthly price increase in 1973 with an average monthly growth rate of near 12%. And we can also see here or observe like this significant price change for wheat and soybeans, soya during the same period, like 73 and 72. So this suggests that in early 70s there were some major, disruptions in global agricultural markets. Yeah, something was wrong in early 70s. So such patterns over here can be further investigated by combining market data with external economic or even geopolitical events. And to tell the truth, I actually did it. I checked what was going on in early 70s, and it occurs that in 1973 there was a global food crisis in the world, which was driven by poor harvests, rapidly growing demand on food, some declining grain reserves, and the oil crisis. So, to sum up, some quite meaningful insight just from this simple query. Okay. So to sum up these queries, I think I showed you that this data warehouse in this system works. So let me show you one last thing. So Tableau dashboard based on this data warehouse. Okay, so this is this final Tableau dashboard, and before I introduce it to you, let's see it in full screen. One moment. Okay, so first thing I would like to show you, these are well, filters. So some interactive controls you can use. So we have like product filter, which allows, of course, users to focus the dashboard on a selected, product, like all or maize, potatoes, rice, soya, and wheat. Then we have year, so we can choose all years or some particular year. And then we have metric selector, so we can choose particular metrics like production, consumption, export, and import. And these filters, they are attached to these KPIs, these 4 KPIs, but also to this charts or maps, right? Okay. So up here we have 4 main KPIs. These KPIs shows the total global, in this case production, here consumption, but also export and import. So all metrics for the selected product in some particular year. So let's change, for example, product name from all to, I don't know, rice. Okay, change to rice, and let's change, for example, year to 1973, maybe. Okay, it changes. There's no data for global rice production and consumption. Import, no production and consumption. Why? I don't know actually. Let's move again to all years. Do we have here? Oh, okay. Yeah, there's some problem with network probably on Tableau Public. I don't know. So 4 main KPIs for different metrics and some filters attached to that. And then we have this world map, and this map visualizes the geographical distribution of selected metrics. So rice, let's change to wheat, for example, and as you can see, it changes global distribution of import, We can change to production, for example. So there's now a global distribution of production for wheat for all years, right? And as I mentioned, this map visualizes, the geographical distribution of a selected metric, such as production, consumption, export, and import, and we can see this distribution across different countries. And it helps identify regional concentration patterns and the largest markets depending on the selected analytical scenario over here. And then we have this tree map, as you can see here. So we have some top countries and they're sharing global metrics, and this tree map highlights the countries with the largest share in a selected metric. Like this time is production. Let's change to export. But once again, it's changing global export for wheat. Let's change, for example, it to maize. So we can see, this, allows us to quickly identify dominant, countries in global production, consumption, export, and okay. I'm not going to analyze the results, but I just want to show you how this dashboard works. Okay, and two last charts over here. They are connected with fact price table. First one on the left, bottom left, we have a heat map, which shows seasonal average price patterns across different products. So here in rows we have different products like maize, rice. Maize is corn, right? Rice, soya, and wheat. We don't have potatoes here because there was a lot of null values for prices for potatoes, so well, there's no potatoes here. And here in columns we have particular months like January, February, March, and so on. So to sum up, this heat map shows seasonal monthly price patterns for the selected agricultural products, which can help analysts identify recurring seasonality trends and some periods of higher or lower commodity prices. And as you probably know, that the more green this squares are, the higher price, right? For example, for rice in January, the average price was $307 dollars, and highest price for rice in May, almost $311, and the lowest price probably on November for rice, $302. And the last one, bottom right, this is like a line chart which shows evolution of top agricultural products, so prices over time. So let's change this maize to all, and now we can see, one moment. Okay, now we can see historical price evolution for this 1, 2, 3, 4, sorry, because this is also prices, so there's no potatoes here. So we can see historical price evolution for this selected 4 commodities or products over multiple decades from 1972 till 2023. And this allows users to compare long-term price trends and major market spikes, like here in 1973 for rice, in 1974. This is another spike here, 2008, for rice, for soya, and other two commodities. So in 2008, so probably some financial crisis affects this product prices. Okay, so that was like quick overview of this Tableau dashboard, and now let's summarize the video, and let's summarize this system. Okay, so to sum up this project, well, allowed me to design and implement a complete serverless AWS-based ETL solution covering ingestion, transformation, warehousing, data validation, CI/CD pipeline, and some BI reporting, BI solution. And this project helped me, gain hands-on experience with, well, production-oriented data engineering practices and some modern cloud-based architectures. And well, three main conclusions and lesson learned from this project for me. First one is that data engineering is much more about architecture and reliability than just writing a Python code. Well, as I probably show you, one of the biggest lessons was understanding that building data pipeline is not only about transforming data. I learned that operational aspects are as just important as the transformation logic itself. Well, second conclusion for me is that raw data is almost never analytics ready. And working with real world external data sets showed me how inconsistent and messy source data can be. And this taught me that data cleaning and standardization are critical parts of every real world ETL pipeline. And the third main conclusion or lesson learned personally for me was that cloud and serverless services, while they simplify infrastructure, but at the same time they introduce some new engineering challenges. While using AWS Lambda and S3, where it significantly reduces the infrastructure complexity and some operational costs, but well, it also introduced some new challenges related to deployment packaging, dependency management, execution limits, and some configuration handling. So it's not like that that you have serverless infrastructure, so you just need to write some code. Well, you need to do a lot more than that. And at the same time, I'm aware of the trade-offs and some constraints of this solution. For example, I build cloud infrastructure with management console, with graphical user interface. Sometimes I use CLI, so command line interface, but I'm aware that there is more effective way to do that with infrastructure as code approach, for example, using framework like Terraform, which I, by the way, use in my next projects. And what else? Another limitation is that the pipeline currently uses full refresh processing and does not support some incremental data loading. And while this approach is sufficient and it's okay for the current project scale, it would become less efficient and harder to scale as data volume grows. So it's not like full data, big data solution. Okay, thank you for watching. I would be happy to discuss these architectural decisions, these trade-offs, or some possible future improvements for this solution. Please do not hesitate to let me know what you like and what you didn't like about this video and about this project. How can I improve this solution? What can be done better? And by better, I mean, faster, cheaper, safer, and so on. And I also invite you to check my other videos in which I will present different and in many dimensions more sophisticated, more advanced data engineering systems. So once again, thanks.